form as what we've used for our other boundary conditions. So let's get ready to run some quasi-static spontaneous rupture simulations. We're going to go back to our favorite examples, 3D Hex 8 suite of examples. The friction examples are steps 10 through 14. 10 and 11 are static simulations with static friction. In step 10, we don't load the fault enough for slip. And so those are the simulations that Matt ran as part of the solvers session. In step 11, we'll run at step 11 in just a minute. And we'll have static friction where we do have slip. We'll skip over 12 and 13, and we'll run, we'll skip over 12, and we'll run step 13 where we have slip weakening with stick-slip behavior. Rather than run step 14, we'll jump, after we look at step 13, we'll go to some dynamic simulations and look at static friction and then rate and state friction. And to run these, as in our other examples within 3D Hex 8, we just run pilot with the name of the .cfg file. I believe I have a couple slides here. So this is step 11. We're going to impose on the x plus and x minus faces, we're going to impose 1 meter of axial compression, and then we're going to put in 3 meters of lateral deformation to load our faults, and we'll end up with left lateral slip on our faults. In step 13, we're going to gradually load the faults, and so we'll impose a velocity boundary condition of 1 centimeter per year on the plus and x and minus x spaces to load the fault. The fault will reach its threshold. It'll slip. It'll stick. And then as we continue to deform the boundary, to move the boundary, the deformation will reload the faults. We'll get another slip event, and I believe we end up with a total of 3 slip events. Any questions before we start running these 2 quasi-static cases? Okay, so let's go here. So I have loaded up my step 11.cfg file. So looking at the top, we have static fault friction, same as example 11, same as example 10, but now we have enough displacement to induce slip on the fault. So static simulation, total time is 0. This is, remember, the step 11.cfg file. We also have all of our common parameters in our pilot app.cfg file that we've gone over several times in earlier sessions, so I'm not going to go over that here. Even though this is a static simulation, I want a reasonable time step to impose so that when I non-dimensionalize my velocities, that things come out, or when I compute my velocities, that I end up with reasonable non-dimensional velocities. And that shows up in some of our more complicated fault constitutive models like the Dietrich-Arena rate state friction. That's more important than what it would be here in our static simulation. So my boundary conditions, again, our favorite boundary conditions on the x positive, x negative, and then lower boundary conditions on the bottom. I'm going to have just my one fault interface. We'll do output on the domain and subdomain. As usual, on my subdomain, I use the output solution subset output component. I'm doing a fault friction problem, so I need to change from my linear solver to the nonlinear solver. And now let's look at our boundary conditions. As I said in the diagram, we're going to, on the x positive face, we're going to constrain the x and y degrees of freedom, 1 meter of axial compression, 3 meters of shear displacement. On our x negative face, also constrain x and y, go 1 meter on the x negative face in the plus x direction for our axial compression, opposite of component as our other face to develop the shear for our 3 meters of lateral deformation. Minus C would again impose 0 vertical deformation. Again, we don't have overlap with our Dirichlet boundary condition or our fault. Here's our fault. We have to change in the default. So default fault cohesive kinematic, we're changing here to our fault cohesive DIN or our fault constitutive model. We have to identify the node set used for our fault surface. So label equals faults. Fault friction model, static friction, friction label, static friction. We need to specify our quadrature scheme, so how we're going to do our finite element intervals on the fault surface. We have a hex mesh, so that means we're using the Fiat Lagrange family of cells on our fault. We have a surface, and so it has a cell dimension of 2. If it was, we're always 1 dimension lower than our main mesh, and so if we had a 2D mesh, and then we'd have our fault was just a line or a curve, we'd have a cell dimension of 1. Our friction coefficient parameters, uniform spatial data, so you notice these are matching up with what I was giving in our slides. So coefficient of friction of 0.6 and 0 pascals for the cohesion. Here's my solver parameters. I'm using specifying a few more parameters than what I had in the slide. So factor shift type non-zero, KSP type, max number of iterations of 25. I expect my fault friction solve to converge very rapidly, but I'm obviously going to check to make sure that it did indeed converge. If I don't converge for that sensitivity solve, then my updates for my tractions will be sort of inconsistent with what I expect, and it's going to be extremely difficult to converge. You know, it's just sort of these sort of converging by luck. And then I have my output parameters. So we're using VTK output. So all we give is just the name of the files. For our subdomain, we have to give it the node set for our ground surface. So that's it for specifying the parameters for our friction model. So let's go over here. I'm in the examples 3D hex 8 directory. Let's run step 11. And I'm going to capture it in a log so that we can look at it. So I'm grabbing all the standard error and standard out into my step11.log file. One things that I like to do is I like to look and see if my nonlinear solve converged. And so I can just do a grep for nonlinear on my log file. And you'll see that it says my nonlinear solve converged due to absolute tolerance in 51 iterations. So let's go in and look a little more closely. So here's all of that initial information about the initialization. Here's now I'm proceeding in my solve. So here's the results of my friction sensitivity solve. It converged when I had very initially with 0 iterations when I had 0 slip. And here's my first main nonlinear iterations. My initial residual is 2 times 10 to the minus 2. My linear preconditioned residual is slightly different from that at 2 to the minus 2. My KSP residual norm goes down to 10 to the minus 12. I converge in 34 iterations. Notice that I converge due to relative tolerance. When I discussed, how we want to converge, I was saying we really want to converge due to absolute tolerance. In this case, I did not impose a relative tolerance of 10 to the minus 20. I only imposed 10 to the minus 10, but it's turning out that this is below my zero tolerance, so I'm actually okay, but it's really not what I would desire in most cases. So we'll fix that and update our .cfg files for future releases to make these things more consistent with what we're advocating. And my first friction sensitivity solve, I converge in 9 iterations. Then once I've figured out what my slip and Lagrange multipliers are to sort of satisfy that initial guess of how much slip I need, then the next iteration I don't need to do any updates. Notice that my nonlinear solve, then the next iteration previously I was at 2 times 10 to the minus 2. I've dropped down an order of magnitude, actually a factor of 20. Now my tolerance, I can end up with a linear tolerance even smaller. Again, 9 iterations. Now I've dropped down to 10 to the minus 5. There I dropped nearly a factor of 30. Now I'm starting to converge a little slower. Now I'm just getting each SNES iteration is going by less than a factor of 10 on 10 to the minus 7. Keep going. Remember, I have a through-going fault, so my updates aren't as good as what they would be if the fault did not go through the entire domain. And so it actually took 51 iterations to converge. Have a very tight tolerance of 1 times 10 to the minus 9, I believe, here as my threshold. It tells me I converged. And notice that I was using here, my absolute tolerance was not very well specified in that I shouldn't need to be doing 34 iterations to push that down to 10 to the minus 19. I should be stopping, I should be cutting them off at, 10 to the minus, probably 10 to the minus 12. So I did a lot more iterations than work than I really needed to, but my solve did converge. And so let's take a look at the results in pair view. So I'm going to load up 80 hexate output. I did step 11. So let's grab the ground surface and the faults. Just a single time step. So there's my ground. Let's see, on the ground surface, let's deform by a factor of, say, 400. Maybe too much. Let's do 200. So there you can see my left lateral slip with no constraints on our Y boundaries. You'll see we do have a little variation in our perpendicular displacements. And if I look at my fault, let's plot what the slip is. So let's bring up a color bar for the slip, color bar for here's my displacement magnitude on the ground surface. So so if I just ask it to put the color bars on the plot, they sit on top of each other, so I can drag it one over to the left, one over to the right. I could try and stack them and change their size. If I ram it up against the top or the side, it'll flip the orientation. So let's stick it over there. There's my slip magnitude, the displacement magnitude. So I remember I'm deformed, move the boundaries each 3 meters, and so that's why I have displacement. My largest displacement to there, and then I have fault slip. And so nowhere do I have a displacement of 0 in terms of magnitude. There's my fault slip with the plus y and minus y faces being traction free. My slip is not uniform. I get more slip in the middle than I do to the sides. And it's about a factor of 2 difference. If I look at my tractions, so faults using my tractions, let's do magnitude in the x direction. So you notice my tractions have sort of the same spatial variation, higher in the middle than they are off to the sides due to my plus and minus y faces being free surfaces. I look at, and so traction x is not the traction in the x direction. That's the first component of my traction. Then when I output the fault is my horizontal lateral shear. If I look at the y direction, that was sort of the up dip, down dip traction. Notice that they are much smaller, about an order of magnitude smaller, and they have sort of the 4 quadrants consistent with sort of the symmetry of my problem. And then my here's my compressive or normal tractions on the fault surface. Negative means I'm in compression, which is what I expect. Greatest in the middle of 20 megapascals, and then decreasing to about 17 megapascals on the edges. That's static coefficient of friction, static slip imposed. Any questions? Okay, let's go on to a looking at step 13. This is a quasistatic problem. We're going to use slip weakening friction. And we're going to go for 200 years. So we're going to load the fault and get stick-slip behavior. So I'm going to use my sort of problem setup is essentially this on the sort of general scheme of things. General layout is the same. I have my same 3 types of boundary conditions. Again, I have 1 fault. I'm going to output things the same. Again, I use a nonlinear solver. One difference here is that now I'm going to use a total time of 200 years with a time step of 5 years. My Dirichlet boundary conditions are slightly different in that now I'm going to have an initial value for what the displacement is. So I'm going to do the 1 meter of compression for my initial value, but then I'm going to impose a constant velocity boundary condition in the shear direction of 1 centimeter per year. So notice that I have, for my Dirichlet boundary condition, I say, here's the components I want. So when I do the initial value, I have to give both components, even though I only have a non-zero value in one direction. Similar with my velocity boundary condition, I need to say that in the x direction, my displacement rate is 0 centimeters per year, but then in the y direction, I have a non-zero value. And then I need to give it this velocity boundary can turn on at a given time, and so that's what this value is. I'm going to turn it on at the beginning of my simulation, so 0 years. So my first time step, I'll have the compression with 0 lateral deformation, and then at each further time step, I'll be incrementing my lateral displacement to load the fault. Minus C face, again, same as what we've had in a number of, almost every single example in this 3D hexate suite. Roller boundary conditions, because I have a fault, I don't allow the overlap with the Dirichlet boundary condition in the fault. Here's my fault parameters. The main difference here is that now I'm switching to the slip weakening friction. here's my flag that's going to force healing at the end of each time step. So all of the weakening occurs within a single time step. This is to get the stick-slip behavior in the quasistatic simulation. And here's my quadrature scheme again. I have my dynamic coefficient of friction, my slip weakening parameter, that's the D0, as well as the cohesion. I'm going to use a cohesion of 0 pascals, slip weakening of 0.2, and dynamic coefficient of friction in this case is 0.4, static coefficient of 0.6. And it looks like we have a question. Is there an example of non-uniform boundary conditions and how to plot the boundary conditions with pair view? And yes, there is. I believe it is in. So our slip in what was that? Step 03, I believe, is our first slip. We may have a uniform slip in that one, but later we have a depth-dependent slip distribution, and in I believe it's step 20, we have a non-uniform traction. And as soon as we run this example, we can take a look at that, and I can show you how to look at the boundary condition in pair view. In terms of Dirichlet boundary conditions, the default Dirichlet boundary condition is for a point-by-point constraint of the displacements, and so we really can't. We don't have support for outputting that at point by point, but there is an additional Dirichlet boundary condition type that is called a Dirichlet boundary condition, and that's for specifying displacements over a boundary. And that there you are given the access to writing out what that displacement field looks like, so you can check to make sure. Obviously, if I ask for in the output what my displacement field looks like, I can then check to make sure that it is matching what I think I've imposed. Good question. Let me make a note of running step 20. Variation in the boundary condition parameters. And so same solver parameters that we had in our last one. Output, now we have time-dependent output. So over the domain, we're just going to do every 20 years. So we have a time step of 5 years in our simulation. We don't want the output of the domain every time step. Let's do every 4th time step. So we are doing 20 years. For the ground surface, we're going to get every single time step in the simulation as output, as well as for the fall. And state variable output will be the same as the domain once every 20 years. Any questions on these parameters for slip weakening friction? Or setting up the parameters for fault friction problem? Okay, let's switch and run step 13. So again, I'm going to capture things to a log when I run on my laptop here with a nonlinear problem that I don't think I save enough lines in my terminal to be able to look at everything. And by also capturing to a log file, dumping to a log file, I can go back later and look at what the solver was doing. It also allows me to run these grep commands on the output so that I can double check very quickly to see what the nonlinear solver, whether it converged every time step, whether linear solve converged at every time step. So with multiple time steps, nonlinear solve, it takes a little bit longer. And so let's look at grep nonlinear in step 13.cfg. Oops. Oh, not the I want to look at the log, not the .cfg file. So here you can see all of the, in every single case here, my nonlinear solver converged to absolute tolerance. You'll notice that I had a number of iterations up here that converged in one iteration. So that's gonna correspond to when the fault is locked, and I don't need to do any nonlinear iterations to update my slip and fault tractions. Then I have several time steps here where I have it takes a few iterations, and so this is when this is when I get just pieces of the fault slipping. Notice I had one iteration here, then I go back to a number of iterations. Things are looking so that the initial time I get slip, I have slip over several iterations. Then in future iterations, things get a little more organized, and I'm getting slip over just a single iteration. So I end up with 4 stick slip events here in step 13 that are in between. I have several time steps of stuck behavior. So if I look at this file, the log file in more detail, again, I have all my quadrature information spitting out. Here's my nonlinear solve. Things not very interesting when I'm getting the stick slip behavior because everything converges in one SNES iteration. Let's just look for SNES. One iteration, one iteration, one iteration, one iteration. Now I'm starting here. You can see that I'm starting to get the nonlinear iterations. Things were converging. You'll notice my friction solve converging in only 5 iterations. Again, my solid tolerances could be improved. I really don't need to be going down to 10 to minus 20. Another stick slip. And so you can look and sort of diagnose to see, make sure everything's converging, examine, how can I, by looking at where my tolerances are, I can pick out, that, oh, I'm still doing relative tolerance, I really should be doing absolute tolerance. And so I'll go in after we look at the results, and we can clean up our tolerances so we can have a better, faster convergence. Let's look at the results of step 13. So I'm going to look at the ground surface and the faults. In the VTK files, you notice that each time step written to a different file. To get all the time steps, I just grab these top files. And so here's my ground surface. So ground surface, let's work by a factor of 200. Let's show just the Y displacements. So initially, here's my time step 0. So I'm just getting the bulging associated with my compression shown there in the X displacement. So I switch that to Y. This is going to be my lateral displacement. Right now, here at time step 0, 0 lateral displacement. That's on the faults. Look at my slip. So, as you'd expect, I slipped here. Initial time step is 0. So let's see. For my ground surface, let's do just the wireframe. So let's make so that you can see it. And so we'll step through. You'll see my boundaries are starting to move. My displacements. One thing we can do is let's plot the displacement vectors. So we'll do a factor of 200 so we can see where we were originally and where we've gone. So this will make it a little bit easier. You can see my lateral deformation increasing. I zoom in, you can we've gotten one stick slip event. I look down here, so if I go back in time, there I had 0 slip, a little bit of stick slip. Displacement, there's another stick slip event, increment in the slip. More lateral deformation, another stick slip event. More lateral deformation, you can see the displacement vector is growing. There's my last slip. You notice that now if I scroll up, and sort of now if I go back from the wireframe to the surface with the edges, there you can clearly see what, if I rewind it now, here's my displacements, they're growing. There's my stick slip behavior, so you can see the discontinuity and displacement across the fault. More loading, there's another stick slip. More loading, stick slip. More loading, stick slip. So any questions in this example? Okay, so what I'm going to do is I'm going to go back and I'm going to try and clean up my solver tolerances, and let's try and get sort of what we really want. So in step 13, here's my PETSI settings. So I'm going to say, let's do KSP relative tolerance equals 1 times 10 to the minus 20. KSP absolute tolerance equals 1.0 e to the minus, let's do 12. Let's play around. Let's do 10. Up here, I'm going to set my 0 tolerance for my faults. Let's say, sorry, down here, 0 tolerance. Let's do e to the minus 10 there. And then, so if that's 10, then we need this to be tighter. So we'll do 10 to the minus 11. A SNES relative tolerance of the minus 20. A SNES absolute tolerance of e to the minus 9. And so let's rerun step 13. And let's capture it in a different one. So running, you can see, we can put it in the background and sort of see where it is. Oh, and it's actually got now. So let's do a grep for nonlinear. And it's step 13b.log. You notice now at the nonlinear solve, I have almost the same behavior. Remember before I was getting 77 iterations. This one bumps up to 78, 77. So, you know, in both cases we converged. And our nonlinear solver looks like it's performing about the same. If we go in and look at what was going on, so let's look for SNES. So we got to go through. You'll notice one difference is that all my linear solves are now taking about 26 iterations and converging to an absolute tolerance. So I'm getting sort of what in the slides when I was advocating for what our solver tolerances should be, that's what we have. So I got to skip through all these cases, time steps where we converge in one iteration. So here's a great example of where I'm going to get some savings compared to what I had before. So first SNES iteration, I took 21 linear iterations and solves for my linears, 21 iterations in my linear solve. Then I cut, as my residual, notice here my starting residual is starting much smaller. And so in order to get down to 10 minus 11, I only take 17 iterations. Iteration 3, it's only 14. And then as I get closer and closer to conversion, I'm taking fewer and fewer iterations. And so my runtime is going to decrease by basically proportional to the amount that I'm able to reduce the number of linear solves. And so that's why sort of playing around with the solver parameters, you can try and reduce the amount of runtime. Make sure you're not just don't immediately go for super tight tolerances unless things aren't converging. And then in that case, you may need to sort of play around with your relative tolerances and then tighten up. So we have another question. Yeah, so there's also terminal commands like piping to T to be able to look at things while you're running step 13. What I tend to do is I tend to capture everything, and then I can use the tail command. And if I want to look at it while I'm running, I can do tail.f, -f, and it'll give me the end and update in real time. Let's see, so I think that's it for step 13. There was a question about spatial variation and boundary conditions. So quickly before going to the dynamic cases while we're in 3D hex state, let's look at step 20. Actually, I think it's step 19 now. So step 19 is a time-dependent problem with norm-on boundary conditions. We apply norm-on traction to the top surface that increase and decrease while applying fixed normal boundary conditions on the lateral sides and bottom of the domain. I also output at arbitrary points in the domain. So let's see here. So on the x positive face, I'm constraining the x degree of freedom, negative face, x degree of freedom, y positive. In negative, I'm doing the y degree of freedom. So on all the boundaries except the top surface, I'm constraining the displacement normal to the boundary. I'm going to impose a change in the traction boundary to the top. It has I'm going to use a query type of linear. It has a simple spatial database that's giving the spatial variation of those tractions, and then there's also a traction time history applied. So I have to tell it that I have a time history, that there is a time history associated with that. The time history is in the file loadcycle.time database, and then I'm going to output in order to be able to see in pair view what that traction change looks like. I'm going to output the change in the value and the change in the start time. It's going to go into a VTK file. This is a norm-on traction boundary condition, so I have quadrature points, and so I'm going to filter those out so I just have one value per cell. A very interesting case is here I'm applying tractions to a boundary that is vertical, and so there's a comment here about how do you detect the orientation of our shear components. In this case, I'm only going to be trying normal traction, so this is very important. But if you are dealing with applying loads to horizontal surfaces, please read the manual for information on how to deal with horizontal surfaces and the shear directions associated with horizontal surfaces. So that's, let's see, let's look at what this tractions, spatial VD, tractions, axial pressure. Let me change the font size for this. So here's a spatial variation in the tractions. And so I said I had a linear variation. So what my field looks like is I have values basically at the perimeter, and then with a value of 0, and then in the middle I have a value of 10. And so Pilot will linearly interpolate between these. And so notice that I am not giving a value at every single grid point. These spatial databases can be independent of my discretization size. They just need to specify the control points for the linear interpolation. I am giving it a data dimension of 2 because I'm going to give it locations on the surface. And then it's going to interpolate in 2 dimensions. For my traction boundary conditions, I need to give it a shear horizontal component, a shear vertical component, a traction normal component, and the time at which to start. You'll notice that these first 3 are megapascals. My shear components are 0. And then the only non-zero value is here in the middle of the domain in the normal direction. I give it a negative value. So if I have a positive value in my time history, that means I'm going to be in the sort of a compressional traction. And then if I have a negative value in my time history, it's going to be in tension. So I had a, let's see, what is it called? It's load cycle. So here's my time dependence. I'm just going to start out at 0. I can have irregularly spaced values in my time history. So it's going to go 0, 1, 1.5, 1, and then back to 0. So it's just going to do an asymmetric loading in terms of it'll do compression and then take that load off. And so let's run this problem. The pilot step 19. Here I'm just letting everything go to the so we'll output standard out. So now if I load things up in pair view, we're going to first look at for step 19. Let's see. Step 19 traction info file. So if I bring that up, this is my ground surface. Here is my traction change times. So notice that next to my value here, I have the little cube, meaning that this is information over my cells. When I have information over the vertices, it's just a little dot. If I look and plot what that is, my change in traction, the time at which I'm changing my tractions is 0, so they're all going to change and start simultaneously. Here's my change in the traction value. So I was saying I had a value, it's going to interpolate from values of 0 out here at the very edges of the boundary to a value of 10 megapascals in the middle. This is the fact that I'm averaging over quadrature points and so forth. You know, there's some, and it's averaged over the cell. There's some variations there from exactly. So in here, instead of getting 10 megapascals, I get sort of 7.8 because there's a linear variation here from the point in the middle where I have 10 megapascals to out here. I've averaged over this cell. And so the average over that cell is giving me my 7.85 megapascals. So that's how I can see what my traction applied. Let's do the whole thing so you can see what the whole domain was doing. Let's exaggerate, I don't know, by a factor of 1,000. See what happens. Let's monitor the displacement. Let's do Z displacement. Let's throw up sort of, let's show my original as a, let's show outline. There we go. So there's my original outline. Then let's advance forward. So let me do my displacements. I need to rescale my there. So if I start at the beginning, let me play it slowly here. Let's try to go back to the beginning. So there, up there, let's exaggerate things by a factor of 4,000. Let's see some deformation. So there we go. Now, so I'll start at the beginning. So spatial variation attractions goes to compression, the thing shrinks down, then we let it release back up, and then it's 0. So that's what a time-dependent traction and being able to look at our boundary conditions looks like. So any questions on that? Okay, I don't see any questions, so let's jump back into our slides for a second here. And so we're going to switch gears and now go to our